So, welcome to this 34th lecture of the CRE series. CRE stands for the Collective for Reimagining Engineering and Innovation. Last 1.5 years, we have been doing a series of talks covering various issues in engineering education and product design and research labs and so on. So Professor Eswaran Subrahmanian and Shyam Sundar, they have initiated this, and then there are a group of faculty from India as well who are participating and supporting this initiative. So coming to today's session, this is going to be on the history of interdisciplinary design at CMU. Professor Eswaran Subrahmanian is the research professor at CMU and part of the Engineering Research Accelerator. He's had a very long experience in with CMU and also looking at several challenges in the industry as well. Some of his areas of research, he's also associated with National Institute for Standards, NIST, and actively involved in the design theory movement and the special interest group of design theory. He is the author of one of the books which is entitled "We Are Not the Users," and it talks about the history of design. So I've requested him to speak about his experience observing this development of the interdisciplinary design group at CMU, which was one of the early initiatives in bringing together an interdisciplinary perspective to design. Today, when we talk about design, there are multiple disciplines within that. There is the product design or industrial design group, there is engineering design, and multiple other fragments of this exist in different forms. But one of the early attempts to look at interdisciplinary design probably happened here under the leadership of Herbert Simon and several others. So putting together or building such a group requires multiple elements to come together, right from the vision to the resources and the kind of people who are coming in to participate in this program. So this is a good experience for all of us to understand. Whoever is involved in institution building, building research centers, and change initiatives within organizations, this will be a very useful experience for all of us to understand. So with that brief overview, I'll invite Professor Eswaran Subrahmanian to make his presentation. Thank you.
Thank you, Sudhir. I just want to mention that during this part of this period of interdisciplinary design at Carnegie Mellon, Professor Shyam Sundar was also at CMU at that time. So he is aware, and he is also aware of the principles and very close relationship with especially Professor Simon. It's my pleasure to give this lecture on the history of interdisciplinary design at Carnegie Mellon. And it has a very long history, as you will see when I tell you the overall story. And in 1935, there was something called the Carnegie Plan. Richard Doherty, who was the president of CMU, talked about moving towards a technical and liberal arts curriculum for engineering and science students. In that, they said a major component of the plan is combined emphasis on the analysis and design in engineering in a sequence of analysis, synthesis, and evaluation courses in which students applied material learned from analysis courses to challenging open-ended design problems in interdisciplinary group projects, in which student experiences the responsibility of leadership and teamwork. This view was implemented by engineers from CMU in collaboration with the faculty at CMU over time, at least the conception and early part of it. If you want to know more, there is a paper called the Engineering Design Research Center, which was published in 1993, which will give you an overview of what was actually done at CMU. So I'll start with Professor Simon's work. Professor Simon has been studying behavior of individuals in organizations as well as aggregate organizational behavior as early as 1942 with his book on administrative behavior. Subsequently, he developed a model of behavioral model of rational choice, the notion of boundedness of rationality, and the concept of satisficing and not optimizing, but satisficing was developed by him. Subsequently, he talked about procedural versus substantive rationality, that substantive rationality is bounded procedurally by computational ability of humans. This led them, along with other work, to the elements of a theory of human problem solving as means ends analysis and goal seeking behavior. And the first thesis was done by Professor Newell. I'll talk to you about him, called The Logic Theorists, which was the first AI thesis, if you want to think of it that way. They developed a computer program to mimic logic in the computer. And they were also, as you see in the picture, Simon and Newell on the left-hand side, they also studied chess, and some of the early programs in chess were also attempted during that period of time. And subsequently, they started developing a programming language for symbolic and numerical processing together. Before that, primarily Fortran, which was a formula translation program, and COBOL were the primary languages in computing. This was a symbolic pattern-based language. Then they also developed a methodology for encoding problem solving called protocol analysis, and developed the idea that given that procedural rationality has computability issues, heuristics become a way of actually solving problems. And then Simon wrote a paper called Architecture of Complexity, where he talked about complex systems as hierarchies of subsystems with near decomposability. This was influenced by general systems theory. And in 1969, the book Sciences of the Artificial, which many of you may have come to see over time, was written, and the book is looking at design as a liberal art, but a rigorous, teachable discipline, part normative, part analytic, and part synthetic. And 1972, the book Human Problem Solving was released, and I have not told you all the story of Herbert Simon, and I'm only telling you part of that is relevant to our context. Alan Newell was his partner in this long journey. Logic Theorist was his thesis with Simon in 1957, and then he wrote the book Human Problem Solving with him. And subsequently, they got the Turing Award in 1975, where they proposed the hypothesis that computer science is an empirical inquiry in symbols and search. And that same notion is embodied in the paper Physical Symbol Systems hypothesis as the notion of intelligence. And as I said earlier, heuristic programming. And Newell was a polymath. He also was a person who designed computers with Gordon Bell. I don't know whether you guys know of a computer called DEC, which used first mini computer. They wrote a book on computer structures and computer architecture with Gordon Bell and Dan Sivoric, whom you will see again. OPS was it's called production system languages. These languages were rule-based languages. If you guys are any of you use rule-based languages, OPS is the origin of all of these. Actually, there was one before that called GPS, but OPS is the real basis for a lot of production system languages. Then SOAR was developed by Newell, and it was called the Unified Theories of Cognition, and it incorporated the notion of learning through chunking. What they mean by that is when you keep applying the same rules over and over, again, you can chunk them into a single rule over time. Newell also looked at the notion of functional reasoning in design with Peter Freeman in the early 80s. Now, Simon was inspired by two main books in the 60s. One is a book called The Notes on Synthesis of Form by Christopher Alexander, who was an architect, and he did his PhD in MIT. And he talked about the notion of hierarchical structure and composition and synthesis from hierarchical structures of the problem that is being solved. I won't go into detail. Alexander then moved away from this notion and developed things like pattern languages, and he has a wonderful 4-book volumes on the nature of order about order in the natural world. And his student Mannheim first developed in 1966 a model of design and planning process from a hierarchical structure point of view. These two were very important pieces, along with the study of cognition and procedural rationality, led Simon towards the sciences of the artificial. Simon and Newell's early influence on design, my ex-colleague Chuck Eastman, who's no more, was the first one to study ill-structured problems. He did cognitive studies of architects, and he wanted to show that it is beyond search. It's a combination of search and retrieval in the case of architectural design. And Omar Aiken did a huge number of cognitive studies of architects to understand the nature of problem solving in architects. And there, the notion of problem formulating the problem and solving the problem was very important in their conception of how design took place in the architectural world. In fact, eventually, Chuck Eastman was responsible for the standards for building design information representation. Now, this had already started, but what had happened was Herb Tour and Herb Simon used to walk to CMU to work, and they started discussing the notion of design and how design should be incorporated in engineering. And Simon's reaction to engineering teaching practices of that time was, one day Herb said something like, "You engineers do a poor job of teaching design, and my book, The Sciences of the Artificial, will show you how to improve things." I agreed about the problem. Design, which is about synthesis, never fitted well into the increasingly analytical engineering curriculum, and it was not thought to be sufficiently scientifically rigorous and researchable to be taken seriously. It was not taught happily by most faculty. This is quote from Tour. He was a chemical engineer. And they decided to apply for an NSF funding in design in the late 60s, but it was rejected, saying that it is interesting, but not in the scope of the Science Foundation. And you can see this is interesting because even though they wanted to do design, design was not taken seriously as a field of researching, as a field of research. Now, with that, I'll go to some more of the history. And what they did was they started hiring people from all over the place. Professor Steve Fenves, who is one of my mentors, he was in University of Illinois. They brought him from there because he was the first person to develop a finite element program called STRESS in 1960s. And he was responsible for starting design and engineering school at CMU. He established the first design research center with Herb Tour. And around the same time, Gary Powers, who is a chemical engineer, had done work on design and risk analysis of chemical process systems, including fault tree analysis, and he became the first director of DRC in 1974 with money from a foundation in the US, and that became the anchor for the Design Research Center at CMU. Then they brought in Professor Dan Sivorek, who's one of the really brilliant people, I have known in my life. He was the first one to work on fault-tolerant computing. He was at he had finished his PhD at Stanford. He was brought from there. Gary Powers came from MIT, and Steve Fenwiss came from the civil engineering department at Illinois. And Professor Sivorick was responsible for identifying a lot of stuff, including instruction sets, fault injection in instruction set, hardware specification language, and I'll show you his research over a period of 30 years later. The first multiprocess, all of your multi-core processors which you use in your computers has origins in CM star, which was a multiple processors working together, and that's the anchor of what today is called the multi-core processors on your computers. Then subsequently, they brought Professor Art Westerberg, who is one of my collaborators for the longest period of almost 25 years. And he had started working on he was one of the first people to use computers in chemical engineering. He's very famous for the algorithm precedence ordering and partitioning for process synthesis, which is used a lot in a lot of places. And he developed a lot of computational optimization method for process design and synthesis. And he also produced a software called a prototype-based modeling language for solving ordinary differential equations and partial differential equation, which was then extended to form an open source software for modeling modeling process systems, especially chemical process system, but it was also used by architects and others. And I think it is still being used by some people in New South Wales in Australia to design solar power systems, solar-based power system. And he was a co-founder of the NDIM project on collaborative design with me, and I'll come to that later. Then Professor Steve Director, who was also in University of Florida with Professor Westerberg, he was also brought in to CMU, and he was one of the earliest pioneers in the computational design of integrated circuits. And the concept he developed was called design-centric, centering for VLSI fabrication. Subsequently, his students went on to build a lot of tools for VLSI design, and he also founded a CAD center for integrated circuit at CMU. Then they brought in Professor Sarosh Talukdar, who was a power systems engineer, and he had done a lot of work on computational and optimization methods for power systems and design synthesis and methods in power systems. And he also worked on power systems market and policy. Sarosh was one of the early people in 1972, 73, when there was an oil crisis. They needed to optimize a lot of power systems in order to reduce the consumption of oil. He used to work for McGraw Edison before he came to CMU, and he joined CMU also as part of the overall sort of people that were brought to CMU to develop this entire design-centric way of thinking about it. As you can already see, all the different disciplines are represented here. Multiple disciplines are represented here in the conception of the Design Research Center. So DRC was there from 1974 to 1986. All students, it used to fund PhD students, but all students were to have advisors from 2 different departments from CMU. So the idea was to develop common basis for design as problem solving. Cognition, computational model of design, diagnostics, asynchronous models of design and control, and computational support systems for design, including languages for modeling. This also led to early expert systems in engineering, civil, chemical, and electrical. All departments in schools except materials and metallurgy, including architecture and Graduate School of Industrial Administration, which is the business school at CMU, were part of this Design Research Center. And one of the main people who was there from the business school was Jerry Thompson, an expert in optimization and mathematical modeling. So the results of early DRC work and subsequent EDRC work led to a whole number of expert systems. One is an expert system for preliminary design, and a catalyst selection system, rule-based system for architectural design, single board computers, knowledge-based alloy design, and also the studies on the nature of expertise of architect, and graphical design environments for quantitative decision models, which was done by Weicha and Henrian. That is really to look at expert elicitation of risk. Many AI techniques were used in expanding VLSI design automation technology. Jim Daniel and many others built that, and then build large-scale software organization, including ArcPlan, which was architectural planning, front-end to engineering expert system. Other work includes design system integration, where design and manufacturing and critique were integrated by Jim Regg et al. And then later on, there was another big PhD thesis on knowledge-based construction for construction and planning by Carlos and Chris Hendrickson. So in 1986-87, the National Science Foundation, the National Academy report came out and was asked by them to study the creation of engineering research center be set in different engineering and manufacturing industries. On-campus centers that would house cross-disciplinary experimental research activities. In addition to the conduct of such research, the principal purposes of these centers are to provide means for bringing together university and industrial people to improve the education of those who will undertake the practice of engineering. That's an important idea, that it has to tie to practice. To expose a significant number of engineering students to the nature and problems of cross-disciplinary research on engineering. This was in 1983 that the National Academy report urged the NSF to set up several engineering research center. This program still continues, and every few years 3 or 4 new centers are created, and some are sunset and the others are new ones are created. And the initial one, there were 6 ERCs, and the ERC for design was created in 1986 with 3 years of funding, with the potential for renewal up to 11 years, and it did run the whole 11-year period with a total budget of $21 million. And the first directors of EDRC were Sarosh Talukdar and Art Westerberg, and subsequently Fritz Perens, who is now a professor at Stanford, was the director, and then Dan Sivorik was the last director of Engineering Design Research Center, after which it transformed into Institute for Complex Engineered Systems. So what is the vision? The vision was to support product life cycle through advances in computer and communication technology to improve the efficiency, quality, and cost. As you can see, one had to think about supporting all of engineering processes, which means if you take the clockwise direction, you are interested in synthesizing different perspectives, starting from perceived need to conceptualization of the product, the feedback, design of the design process, organization, etc. And through this process, you did the synthesis of the project. Meanwhile, in order to accommodate all these different perspectives from the latter part of the design, you need to create abstractions which could be used as part of the design process. And you can see abstraction is from the latter stages, and synthesis is right from the two. These two cycles were operating together in product life cycle of any artifact. The 4 principal goals of Engineering Design Research Center were to make a significant contribution to design science in the form of methodologies, computational tools, and environments for engineering design, to educate a new generation of engineering design practitioners, educators, and researchers for industry and academia, to infuse the engineering curriculum with engineering design textbooks and other course material and courses, and an optional undergraduate minor in engineering design, to collaborate with industry to support improved design practice by exchanging knowledge, people, and software. And you will see in the rest of the talk how all of these goals were achieved to varying extents by the center. So how did we think about planning this entire center? And the planning of the strategic plan for the center was done with the help of a very senior person, vice president of Alcoa at the Aluminum Company of America, who came every week to our center and helped us develop a strategic plan, because this was usually academics only work on near-term projects and they are not very good at developing long-term strategic plan. So he came and helped us really develop the entire strategic plan, and you will see it as it got developed. The arrow in between, it'll get filled as I show you. What was the idea? The goals were to create unified representation of goals, constraints, and behavior that will help with the fundamentals of design research. Then you have computer-aided design, where you are interested in creating comprehensive single domain test beds, leading to increased product cycle coverage, and integrated design environment, which are multi-designer, multi-domain test beds, and develop multi-designer, multi-domain environment where people can work. And this work is still going on, actually. Okay, what are the questions and challenges as framed? Given the usually very large number of alternatives for synthesizing a design, how can representation of design spaces and search algorithm be used to effectively examine many design alternatives? Here, decision theory, problem solving, and heuristics were the core of the generation and choice of alternatives. Then how do we process qualitative knowledge in design that is often diverse, incomplete, and often uncertain in nature? So this is where decision and preference under uncertainty and ambiguity became the focus of the research. Since the design of engineering systems require both qualitative and quantitative evaluation, how do we combine paradigms of qualitative reasoning with quantitative analysis and optimization? Here, integration of logical and numerical system were very important. And actually, Professor Simon wrote a paper called Two Heads Are Better Than One, where he argued the computational approach with heuristics for design as well as optimization methods should be brought together. That's where the logical, symbolic, and numerical world were to be brought together. How can we account for coupling of decisions and complex analysis model that usually prevent straightforward decomposition of synthesis problems? That means beyond near decomposability, all problems are not just decomposable, they are only nearly decomposable. When they are not nearly decomposable, how do you deal with it at the interfaces? What are the issues in the interfaces that are faced by designers when you break down the problem and recompose the problem in terms of synthesizing the solution to the problem? How can learning by human beings and by computer tools be performed to improve the design form process? All of you learn a lot about machine learning. This idea already existed. Machine learning and learning from doing to creativity. All this entire spectrum of questions and challenges is how the questions for the center were framed. Now, I'm going to give you a laboratory by laboratory strategic plan. This is design synthesis laboratory. So you can see on the left-hand side how can we have computational design critics? How can we have knowledge-based synthesis? And then how can we create domain-specific modeling environments, including geometric reasoning and representation and optimization synthetic techniques? Now you can see that the knowledge-based synthesis, form function synthesis, learning, formal process of innovation will enhance the design science. Similarly, form and function synthesis will lead to combined AI and optimization. And similarly, we also bring from our optimization world the large-scale model solutions and computational models of design and rapid prototyping, which will lead to multi-designer, multi-domain environments. So as you can see, the strategic plan really gave a way for us to look at how to develop the research questions and how one set of research questions sit on top of other research questions that form the basis for design synthesis laboratory. Design Synthesis Laboratory was held by Professor Ignacio Grossman, who's one of the leading chemical engineers in process optimizations in the world, and there are several students of his who are in India too. So in chemical engineering, this whole thrust was led by Professor Biegler, Grossman, and Westerberg. In power systems engineering, it was done by Sarosh Talukdar, and structural design optimization, Steve Fenmis and Art Westerberg. This is interesting because civil engineers didn't think of optimization as one of the tools they have available for them. And here was a cross-pollination of chemical engineering and civil engineering in arriving at optimization methods in civil engineering. And in the process, they developed a whole bunch of algorithms, mixed integer linear programming, mixed integer nonlinear programming, combined discrete and continuous variables in chemical engineering. So currently, these methods are used extensively in industry to optimize structure for process optimization. Numerous tools, models were developed for this application. And Ascend, an advanced system for computation and engineering, a toolkit that was developed for modeling processes at different levels of abstraction and analyzing them using ODEs and PDEs. Then it was designed for manufacturing laboratory. Fritz Prinz, who's a physicist, mechanical engineer, was the director. And here also you can see there are certain things were brought together, form function synthesis, and then geometric representation, rapid prototyping, rapid manufacturing, and then functional assembly, material design and selection, and similarly representation and management of design information, general design representations, and all of these led to also including rapid prototyping, such as what you call maker spaces of shape deposition manufacturing was also developed during this period. This was led by Professor Fritz Prinz. And the shape deposition manufacturing was led by Lee Weiss. Unfortunately, he passed away a few years ago. He was one of the earliest people to actually do shape deposition manufacturing. So they could do shape by depositing material layer by layer. They could produce these impeller designs, and this is one of the earliest work, along with some people at MIT, to really create shape deposition manufacturing. And today you see all over the place maker labs with 3D printing. This was the early part of the 3D printing. It was not called 3D printing. It was called shape deposition manufacturing at that time. This is a brilliant figure, as you will see, Dan Suvarik's work. He started with the idea of modular design, which led to multiprocessor design, which led to performance evaluation and parallel programming, which is what has led to today's multiprocessor chips, which you have all came out. And as you can see, how research and industrial impact or commercial applications are tightly combined. Similarly, he worked with Lee Weiss and Fritz Prinz in actually creating some of the what do you call, some of the single board computers, early single board computers called Micron, which had both shape deposition manufacturing for casing of the computer, and at the same time developing other material, other circuit design and single board computer design, and those two were brought together. And as you can see, especially in Rand's work, is really telling, is how from 1972, as he went towards 1990, many of these things became part of the industrial landscape, and today they are in the background. Rather, they have become the they're not novel as much as they are part of the scene, day-to-day scene of today's applications. And Dan was also responsible for developing some of the earliest generation of wearable computer, the Viewman 1, bulky machine with a headset for looking through the, visualize the pieces through the headset, like the Google Lens or Google spectacles you have seen. And this is the second generation and the third generation. Fourth generation, and something called Navigator was developed, and Navigator 2 was developed for aircraft maintenance for Boeing. So you had a head-mounted display. In this case, the user not only sees the aircraft maintenance interface, but it is overlaid on the work environment so that the maintainer can actually see what to do and how to actually perform the task. To give you an idea, you can see it's really wonderful because you have miniature displays, speech recognition, language translation, microprocessors, and wireless communication. Viewman 1 was miniature displays primarily and some speech recognition. As it went on, it it was developed for smart buildings and manufacturing, and for plant operation, for language translation, and for maintenance, for medical applications, invisible computing in smart rooms. And there were a lot of new concepts that were developed. Think about it, 1998, they were already envisioning the notion of foldable displays, which is what you find in your new Samsung flip phone. And it took over 20 years for DuPont to develop the right material so that you can do foldable displays. But they had already started thinking of these kind of things, these kind of devices, and the digital ink is what you write on your iPad. When you write on your iPad, the idea of a digital TIM came, and for navigation. So you can see how different pieces were brought together in creating an entire variety of new ways of thinking and uh, supporting people at work, in their work. Okay. In fact, some of these things, like the maintenance and language translation, was used in Bosnia when Americans were at war to allow the troops to talk to the local people with a wearable device. Then Design Systems Laboratory was run by Professor Sarosh Talukdar, where the notion of design critics, integration, domain-specific modeling environments, information management, process management, human-computer interaction, design knowledge compilation, and general design representation. And this also was connected with rapid prototyping. These were the thrust areas. As you can see, many of these thrust areas overlap across the labs as a way to actually create synergies across these labs and come up with new ideas and innovative designs. Sarosh also developed something called distributed problem solving kernel, which allowed for multiple methods to be combined, multiple optimizations to be combined in the same platform. So you could use mixed integer linear programming, you could use other nonlinear programming tools, they all could cooperate and work together. One of his contributions is called A-teams, asynchronous team, allowing for asynchronous problem solving. This was implemented for power systems, in chemical engineering synthesis, and eventually it was used by IBM for scheduling steel mill production with both humans and the optimizing systems as part of the distributed problem solving team. And subsequently, we were asked to build by a gentleman from Westinghouse who came to us and said, analysis tools are not just part of engineering, but they are part of a larger notion of collective work in designing. So we were introduced to ethnographic methods, and we started using ethnographic methods in studying actually how design takes place in a collective environment. So from that, the hypothesis that came out was designing is both a cognitive creation of formal and informal representational structures and social activity, negotiation, creation, and validation that is emergent over time, punctuated by temporary closures. Designing involves the evolution of the artifact, the process, and information models in context. The reason why it is called NDIM is n-dimensional information modeling. Each perspective bringing a different set of models, a manufacturing model, a marketing model, a design model, all of these are different models. But when you actually design an artifact, all of these things are interacting with each other. How do we build support for this was the primary question behind this project. Rather, it's the logic of collaborative design or the logic of the collective in the collaborative design. So if you want to think of it, there are individual views, there are different pieces, functional models, project activity models, intermodal relationship, revisions and access, and tool execution models. And you had all these libraries, and you could compose them on demand by the individual designer as per their own perspective. This was the vision. How did we come to this? We actually studied engineering. We studied how Bosch produced consumer product by looking at information flows and also the different representational structures that was exchanged by the different participants in the design process. On your right, you see it's airport trains. We studied airport trains, and you can see the entire design process looks like a complicated circuit. And we had to worry about the issue of how to deal with change management in this particular case, because these trains last for 30 years and technology changes and you have to manage the change. So I just have given you some ideas of the interfaces to the systems we built. We built for ABB first, and then Bosch, and then Adtran, and many of these systems are implemented and being used in the respective companies since that time, with modifications thereof. What kind of things were built? Several support tools were built. This is a short list of examples. Ascend was advanced modeling for equations. And then DICOPT was MINLP, is mixed integer nonlinear programming. And NDIM was for information and process management. SEED, software environment for early building design, optimization models, 3 orders of magnitude improvement for large-scale modeling and solution algorithm. We did tools for shape optimization, thermal analysis for variable computer design, CAD models for shape deposition, asynchronous teams, and toxicity measure for plant emissions, input-output lifecycle assessment method for products, and computational aid for environmental standards, and many other support tools. Industrial impact. ABB, Integrated Collaborative Environment for Transformer Design, was built as a prototype with the engineers at ABB after studying their information processes, and then it was transferred into the industry. Similarly, with Bosch, was for collaborative design information management, and AEG, rather ATRANS, it was design process, integration of information across labs and shape deposition manufacturing with Alcoa, Boeing wearable computers for maintenance, DARPA wearable computer for language translation in Bosnia, Eastman Kodak tools and algorithms for process design, and with GM it was design support for simultaneous engineering and shape deposition manufacturing. New courses, Synthesis and Engineering Design was developed by Professor Grossman and Fenwes. Distributed problem-solving courses were developed by Sarosh Talukdar. An interdisciplinary product design course was developed by Professor Westerberg and myself, where the entire university, students from the entire university could participate. So we had students from English, industrial design, art, all the engineering, computer science, etc. And we also developed another course which is called Engineering Problem Formulation and Social Context. It was Talukdar, myself, and Westerberg, and we ran this course half the students in Netherlands and half the students in the US, so that people understand the social context in which engineering problems are created and solved. So it was a very important course. And subsequently, there was another course on joint product design with industrial design and mechanical engineering with Fritz Prinz and later John Kagan and the faculty from industrial design. So this is the summary of the entire process. As you can see, the places where it is crossed, those were things where we accomplished most of our work. And the rest of it was still open, and it is still open in a sense to think about comprehensive process design, comprehensive computational models of design, and product design for the environment. As you know, these are all still open questions, and this still continues in various forms. And there were 180 reports and 80 PhD theses over 11 years. I want to close the lecture by thanking all of those from all over the world I met, because in my corridor there were people from 20 different countries in our EDRC building, and I met and worked with DRC, EDRC, and CMU from academia and industry, and for the interdisciplinary experience it provided me and to all of those who walked through.
Thank you for a very detailed presentation on the history of design at CMU. I have some questions, but we will open the floor for questions from the audience. Then we will take it up. Any questions from the participants?
This is Shyam Sudhir.
Please,
Shyam
please.
Sudhir.
Go ahead.
It's not really a question, but I'm glad, Sub, you started out with the Doherty plan, and I think at CMU the new approach to entire engineering education implemented in the 1940s had a major impact in how the university was organized and the culture of the university of cross disciplinary and departmental work, which became the norm for the entire university, whether it was engineering or management or philosophy or even architecture. And I remember attending that one of the workshops at EDRC on must be early 90s on variable computer design. And not being a computer design person, I was really pleasantly surprised how far ahead the group was thinking in terms of design and integration of very varying ideas. And I had many conversations with Sarosh Talukdar first with his work. So I think that if we, it's probably worth mentioning that lowering the boundaries between the departments and various schools, even across engineering and other schools at CMU, was very important to the nature of this endeavor and its success at CMU. And question is to what extent the organization of engineering institutions and universities in general in India permits that kind of collaboration and extension beyond departmental and school boundaries. Thank you.
I just want to make a remark. EDRC was the first ever cross-disciplinary design research center in the world. EDRC as an NSF center. After EDRC was set up, EDC in Cambridge was set up. Cambridge and Strathclyde and 3 universities in UK, and a similar center was set up in University of Tokyo called a Research into Artifact Centered Design. So it was not only CMU, the impact of what CMU did was global in understanding design as a comprehensive interdisciplinary field where through the lens of computation, interdisciplinarity could find another space of interlinkages in common methods and common ways of addressing engineering problems. You can see that is how design science and design theories evolved in this context. So it's really a rich environment, as Shyam pointed out, creating an environment in which a lot of the ideas and other things could come together. And all of the people I mentioned, they all work together as a community. I started in EDRC as a researcher in 1984. 6 years before that, I was still involved. Even though I was not directly involved, I still used to go to their meetings. And subsequently, my entire career in terms of thinking about interdisciplinarity and bringing different disciplines together was formed. And many people, as you saw the number of students who graduated, have gone out with this spirit.
You mentioned about NSF funding for EDRC, but prior to that, NSF did not recognize design as one of the areas. So what led to this NSF to really start looking at engineering, supporting engineering design?
Primarily, there is if you go back, I can point to you, there is a National Academy report, National Academy of Engineering report. And this was the time in the mid-80s when Japanese were producing cars and sending cars to America, and American manufacturing and industry was worried about it. And Dale Compton from Purdue University was at the National Academy of Engineering. So he convened a bunch of people and asked, what is that we need to do in engineering to be competitive in the world? And in that, what was proposed by NSF was to create these engineering centers. This engineering design center was one, in net shape manufacturing was another one, engineering of materials was a third one. As I said, there are 6 ERCs that were created. Since then, there have been over 30 to 35 ERCs in bioengineering and other things in different universities. And remember, after 3 years, if you're not performing, the funding gets cut automatically. You are given 3-year extensions. And we managed to get the entire 11-year extension to do that. And the idea is after 11 years, you would become sort of self-sustaining. It's very difficult to become self-sustaining. So after 11 years, the Pennsylvania government, under the Pennsylvania Infrastructure Technology Alliance, they still give $2 million a year to promote interdisciplinary work at CMU. and at Lehigh, which was an engineering research center for structural design, structural and civil engineering design. It requires, it's like growing a plant. You have to pour water all the time and encourage and create a cultural space in which people feel comfortable to talk to each other, critique each other, find common grounds with each other. And this is a very important, and I've given this presentation in Europe, and people are astonished that in the early 80s, rather late 70s and early 80s, CMU had already started thinking of this kind of multidisciplinarity and creating ways in the institution, in fact, including very interesting accounting methods by which credit can be given to everybody, was developed. So it's really a design of an organizational structure, the incentive structure, all of those are and funding structure are integral to this kind of an endeavor to take place and take root in a fashion that it can have serious impact in the society.
So one of the parallels that I can draw with similar initiatives in India is on the industry side, TCS was probably the early one to set up what is called a Tata Research Design and Development Center. So they brought design between research and development. This happened in 1982. And essentially they were focusing on combining software engineering and systems engineering as a basis for all the services work that they do. Right? And one of the people, Professor K.V. Nori, had actually spent some time at CMU, and he was brought into this group. I don't know whether there is some connection there, but that was one example. The other example is in an academic sense, an attempt to build this kind of interdisciplinary center is the setting up this IIIT DMs, to which I belong right now. This was conceptualized in 2003 with an idea that can India, because of its established IT base, can it combine IT and design to make manufacturing more competitive? Right, which from the presentation that you made of bringing IT across the product development life cycle, I think some of those ideas were initially seeded, along with combining product design as well. That is the aesthetic element as well. So that was the view with which these institutions were created. So yeah, some parallels in that. But
in fact, I can go as far as to say Professor Balan Gurumurthy at IISc is a product of EDRC. That's what led him eventually to create CPDM or whatever, product design and Center for Product Design and Manufacturing. And one of the other people, Amrish, is a graduate of EDC from Cambridge. And you can see the effect of CMU has been quite strong across the world, including in India at IISc, to give an example with Guru's effort with establishing CPDM.
any questions
Hello.
from the
Hello.
participants?
Yeah,
Please.
I am Kishore Hurchandi from VNIT Nagpur. I am really happy that institutes like IIIT DM, they are working in the domain of integrating engineering and product design. In fact, after the technology works, designing a sellable product is the next huge domain. We have been making, technologies, we have been designing products in our laboratories, but when it comes to converting to products, it miserably fails due to various reasons. Unfortunately, what I have observed is that the costs for converting the technologies into sellable products, they are too high in India. Might be that the actual ecosystem for converting the technologies into product is not available. And can we get such support from institutes like IIIT DM or IISc Bangalore? Some of the companies, they are doing it, but they are least interested in supporting academic institutes. So we are looking forward to institutes like IIIT-DM or IISc Bangalore, who can help us, in this venture. So,
yeah, I don't think anybody from IISc is here in this talk, but you may want to talk to them. They have been successful partially in moving some ideas into the industry, but I don't know how much they have been able to really create products. Creating products, even from CMU point of view, was not easy. Sure, Sham, go ahead.
I just want to say that the cases that I have seen which succeed or don't succeed, when you compare them, the most often you find that the design was developed or exclusively or mostly in the engineering domain with little feedback, little involvement of the users, ultimate users of that product, and little market research and pricing research into whether that design, and of course, manufacturability research. And so I think when we say that designs are too expensive to produce and take it to the market, that is mostly, in my experience, because design has not taken the market into account. Design has not taken manufacturing, the cost, and the pricing and marketability and user preferences into account. And so design requires more than engineering designers. It requires involvement of an entire chain from engineers down the road to the users.
Very much so. Very much so. One of the things that happened in the wearable computer, as you noticed, as I mentioned, the recipients of our technology were Boeing. They had a problem of improving maintenance. The US Army had a problem of sending soldiers who can't speak the local language. And how can they carry these wearable computers? So CMU itself produced about 30 to 40 of them to be given to the military to be used in the field so that they can learn better as to how exactly to make these systems better, design them better and improve them. It's a continuous process. As I said, design is a series of temporary closures where you bring different disciplines and different pieces together with an openness. Okay, so you have to have open dialogues between the different participants in the design process, from the client to the company to the researcher and so on. And this is where design is a process of dialogues of bringing different disciplines together to solve a problem. Yes, you can also solve specific problems in terms of developing methods. That is one part. There is pieces and the whole. We need, just as designing is designing of the parts and the whole, designing a curriculum, designing a center is also bringing the parts and the whole together so that a whole which can be conceived or could not be conceived before could be conceived. We would have never come to wearable computers if we didn't have such an environment where we could bring mechanical engineers, shape deposition manufacturing, circuit designers, industrial designers, and everybody together to address the problem.
I'd like to learn more from Mr. Bhurchandi about
sure.
situations that he had in mind, and who were the people involved in the design, were the makers, marketers, users involved in the design?
Sir, we had support from some industries, but here the scenario is like, I mean, if you go to industry with some technical design, technical product, and you ask them to support, they will simply say that you just give it to us, and they will try to offer us some meager amount. But here, yet the culture of joint working is not I mean available. So everything we have to do on our own, right from technology design to product design to, I mean, everything.
Yeah, so the one of the issues is the translating from certain level of TRL to where the industry feels comfortable with that. That is also needs a lot of resources, and in a
Yeah,
pure academic environment, mobilizing that resources itself is a challenge unless you have a
exactly,
clear customer who is interested in that, right?
exactly.
And that is
And
where
if the
one of
customer
the
is there,
things,
and if
yeah,
the
no,
customer
one of
is
the
there, if the customer is there who is clearly interested in our product, he will I mean try to keep our institute aside, and he will simply ask to hand over the all the rights and everything to them without I mean much of any liability on them.
no. So when it comes to IPR policies, some of them can be negotiated. But what also is a opportunity which is today emerging is the emergence of the nascent entrepreneurial ecosystem in institutions. So whether these entrepreneurs can become the bridge between these two sides is something one can try and explore, because there is some amount of funding support given to startups, and whether startups can help bridge this gap between the technologies created by the institution and what the market requirements are. That is an alternative channel to explore in at least in an Indian context. But expecting an institute to fund and translate the technology into something which is really ready for market, I don't think that kind of approach or investments that an institute is really designed to make, right? And like for example, institutes do have corpus which can be used for research purposes and so on, but whether they can really use that same funds to build or invest into technology development, I think there are gaps there.
Yeah, that is exactly the issue.
The
So we have run out of time, 10 minutes more. Any one more question if people have, any participant has, we can take.
You are welcome to write to me. My email is sub@cmu.edu. And
Yeah.
I think this is a very rich area. I can give a talk for another 2 hours about all the various things we did and how it worked. As I said, in my corridor, there were students from different countries and different disciplines. I interacted with engineers of all kinds and industrial design and so on. So I think it is really a cultural issue which has to be addressed both internally in the institution as well as with the society. You know? And unfortunately, our industrial groups have to look forward into saying, hey, there is going to be something new that is going to come which I can adopt. Or it may take 10 years before Google Glass came and it failed. But then now Oculus and all kinds of other things have come. So you cannot always anticipate that something you are producing is going to have an effect right away. But as long as you are involved with industry and others, it provides the seed for them to take it and run at some point in terms of the real impact. And you're absolutely right about intellectual property. I just will make a quick remark. In our product design course, all the projects were sponsored by industry. We had an industry person working with the students for the entire semester, and any IP that came out of it could be taken by the industry for 1 year, provided they continue supporting the product design course, number one. Number two, if they don't use it after 1 year, the intellectual property reverts to the university, and the university has a right to continuously evolve the product over time, irrespective of what the industry took at a particular point in time. This makes the industry want to be involved with the university because they are getting free research and free development done, essentially free. They used to pay us $15,000 a semester to participate in these courses. So with that, it's a complicated issue. We need to worry about those things. Yeah.
Yeah. So thank you, Sub, for taking time and sharing your experience on this evolution of design at CMU. For all the viewers, the next CRE talk will be on 11th September, same time, 6:30 p.m. It will be by Professor
Sebastian Myers.
From KTH, Sweden. So we will announce the talk as we come closer to the date. So feel free to join that talk, which will be on 11th September.
Thank you, Sugidhir.
Thank you, sir.
Thank you, sir.